than something
that becomes the new.
What if
Yeah,
like,
yeah, or like a max, like if it's bigger than this one, you just replace the core.
Yeah, that's what I mean.
That like, there's a list of 10 particles, and you get a new particle, and it's bigger than any of those, and but it's smaller, you put it in like small.
like how, what about like, well,
That's
yeah, that's no, I don't think we did well, move it to the top. Yes. Move to the top, it's like just like.
Prior to queue
Like
interface,
compare like the value like.
get smallest, remove smallest size.
That's smart. But no, that, probably the runtime would be crazy.
You record like the way that.
Yeah, a fixed number of particles we have to
And
record,
then.
like,
change
we're
it.
given like. And like infinite amount or like millions of particles,
Well, you
we need to do a
can
turn
do it.
amount, which is like fixed length. But
Still.
like what you said, we have to like compare them to see if it's, you know, pop this one off if it's small or it's bigger.
All right, what do we get for ideas? Alex, what'd you say?
I said like maybe like create like a stack type of thing.
Okay.
Compare like the amount of energy and like if it's greater then you move it up. But I feel like that would be like a lot more big run time.
Okay, so you're creating a stack, and when something comes in, if it's bigger than everything else, you're putting it at the top of the stack?
Yeah.
How do you put anything into the middle of a stack? What do I interact with a stack? It's an interesting idea, but where do I interact with a stack?
It's all out, yeah.
Just the top. Can I insert something?
No.
No, I can't. I mean, it's an interesting idea, right? If I can insert something 11 things down, right? If it weren't the biggest of 10 things, I could stick it to spot 11. Can't do that with a stack.
Yeah.
Other ideas.
Well, we thought that like, we could like track like each time some. Well, I don't think it's gonna be that good because it'll only be like the greatest and smallest, but each time something comes in, we could like. Compare to like the greatest or smallest and like have like that in like the pointer or something, and then we could return that. But then the problem with doing that is I'm not sure like if that's found, and then what if they want to find like the next, like let's say.
Yeah, we want the 10 biggest things, not just the biggest thing, right? So you have the biggest thing.
So we would probably have to like sort.
So one thing we could do is take them all in, sort them, and just grab the top 10. Right? We could do that. You all come up with something?
Yeah, similar.
What? To what?
The way that just not enough. They just not enough.
Keep track of everything.
Yeah, larger than they-
Well, keeping track of the largest or keeping track of everything?
Oh, we only talk about the largest.
Okay. All right, any other thoughts here? So, right, so we create a list of all particles, sort it, return the M with the highest energy. Okay, what's the problem with that?
I feel like a million particles to sort it.
How fast can we sort things? Can we sort things in log n?
And long.
N log n. So our fastest sorting is n log n. Is that problematic? Sorting, I mean, do we have to sort a million things all the time? Are computers good at sort? What do computers do mostly? In other words, what's another word for arranging data? Sorting. That's what computers do, right? So let me see. I can't find my. I need to be able to find either one of these things now.
And log in is a good one.
N log n is great long runtime. Yes.
Like log in.
Is log n is absolutely better. Yes. But can we get log n with a sort? There you go. Okay. So n log n. We're gonna do a million things. How long do we think it's gonna take? 2 seconds for a million things?
Like probably like 2 hours.
2 hours? Yeah, 2 seconds to 2 hours. Anyone want to go in between?
10 minutes.
10 minutes?
2 minutes.
2 days.
2 minutes? 2 days?
10 seconds.
5 minutes? 20 seconds. Can we wait 20 seconds to sort a million things? Yeah, we could probably hold off on that, right? Yeah, n is 1 second. Okay, if we add but n log n is 20 seconds. Can we sort in n time?
No.
Okay, somewhere between 1 and 20 seconds for a million things. So the sorting is not a big deal. We could do this. What's a bigger issue? How long is our array? A million things, i.e. fair amount of memory, right? So it's not ideal. We could do it, 20, we got to sort it, so it's not necessarily the best. So let's think like as computer scientists, we want to think about the most efficient way we can think of. Yeah.
Could we just highlight, since we only need to record the end, we just have like a fixed length array and then just compare stuff as it comes in and just, so it's not just throw it away.
So we could, so you're thinking about like, okay, we have an array. Let's assume this is 10 long. We've got the 10 largest things. Something comes in. If it's bigger than the 10th largest thing, put it in the array, take the other thing off.
Yeah.
That would totally work. Yeah. That would totally work, right? So now we only are keeping an array of 10 things. And what do we have to do each time? Which isn't that big a deal. We have to compare each time. And could we compare just to the smallest thing of the 10?
Does it say we can give it an order? Like,
They have to be the 10 largest things. So we would have to figure out a way to keep like,
yeah,
you wouldn't just have to compare. So let's say I threw something in here and it were
that's true.
9.
It'd have to go between.
Let's say the 10, we're doing it for the 10 smallest things. Let's pretend it's the 10 smallest things. And I say we're gonna throw 9 in or 7 in here. Can I just swap out 7 and 13? No, I can't. This would have to be sorted every time, right? Why would it have to be sorted every time?
So that we know where to put it.
Yeah, because then if 7 came in and I put it here and then I got 8.5 or 7.5. Sorry, my numbers aren't very good for this example, right? I would say I got 6. So if I had 6 here and I got 7, I would think, oh, 7's not gonna be in the list, but it should be, right? Does that make sense? So I'd have to, when I put this thing in, I'd have to slide it to the right place. So I'm almost doing a selection sort or an insertion sort, right, as I go through, which isn't ideal.
But isn't that a lot better than just doing like? It's way better to just look at like 10 things and then out of like a million, right?
Is this better than our naive approach? Yes, totally better, right? Because then all I'm doing, instead of sorting and comparing a million things at the end, I'm sorting and comparing 10 things each time.
Yeah, but it's still like.
Well, you gotta figure, if things came in increasing order, it depends how these particles are coming in. If the particles are coming in smaller and smaller, getting bigger and bigger, I'm doing a ton of comparisons over time, right? But if they're sort of random, it's probably gonna work out okay. And it's certainly better, as Logan said, than having a million things and doing it that way. But there's a better alternative here, okay? So this is the naive implementation we just said. So we got an array list of particles. He's got some sort of weird for loop with a timer that's timing things as they come in. We're going to add all the particles to this all particles array list. We've got a comparator in here, and then we sort everything and we give out our sublist from 0 to m. This is just sort of a pseudo-ish code of how the entire array of a million things and sorting it. Okay. Huge amount of memory when n is really large. Okay. Can we do this in O of m memory with a min PQ? So similar to this structure, okay, but we're going to restructure it a little bit so that we don't have to do all of the steps that we just did. Okay. So instead of doing that, we're going to have a min PQ. So first of all, we're going to have a comparator. Okay. We're going to have a min PQ of particles, high energy particles. Okay. We're going to pass in the comparator here. We haven't really seen this yet, but we will. Iterate through. And then what do we think we want to do here? If we have a min PQ, and all you know about a min PQ is what? Turns the smallest thing off the top.
Oh, if we're doing the particle comparison,
Mm-hmm.
we return that, then we compare that, and if it's bigger, right, then we just insert it and we're done.
One more time. Whoa.
And then return the smallest thing from our fixed, like list of m particles. right?
But this isn't going through our fixed, we're not combining the ideas. This is a stream of particles. It's coming in, right? We're getting these things, 1,000,000 particles. We're trying to keep track of the 10 largest. How can I use a min PQ to do it? You guys can close your computers because whatever you're looking at isn't this.
Which one is the smallest thing and we want the end biggest?
We want the largest things. What do you mean a reverse
Is
method?
it like right? Could we like go
Probably not, but
around?
I was just thinking about like, if there's like some kind of like reverse method that you could do like.
Well, you could do a max PQ, so you can make it the maximum thing coming out of it. That's possible. Well, if we go back and look at our interface, this is it. We can remove the smallest, we can get the smallest, we can add.
And wouldn't you just do like max speaking?
Well, in that case, we would be able to get the largest and remove the largest. So, yeah, right?
Could you just delete stuff until you get it?
So how big do we want our men PQ to be? How big do we want our bag to be? We got a bag, we're throwing things in it. Someone just said it. M things. So if we want the 10 largest things, I've got a bag, a min PQ, that's 10 things. And then what?
We just keep it 10 things by
So we keep the 10 things and then remove the smallest.
Yeah. Right? So it'd probably would it be 10 things or 11 things in the bag? Theoretically.
Would be 11 things and then you remove.
Yeah. Right? So all we're going to do is we're going to go in. So we're going to go through. We've got this min PQ of high energy particles. We iterate through. We're going to add every particle as it comes through. Right? Then we're going to see if the size of the particle is greater than M. And then we're just going to remove the smallest. So every particle that comes in, we throw it in the bag. Right? If it's the smallest thing, what do? Take it back out. Okay. And then when we're done, what do we have though? This is sort of one final trick that you need to remember with min PQ. We've got a collection of 10 things in there. Yeah, so we've just got a collection of 10 things. So what you would ultimately want to do at the end is create an array list, pop out the things, and you'd have them in order. That's the other thing about using a min PQ is you can have things, you can use this as a sorting algorithm, right? Because if you think about what I've got in the bag, what's the first thing that comes out?
Awesome.
The smallest of the greatest 10 things,
Oh, that's
right? And I pull out the 10 things and I just add them to an array list. And now I have a sorted array of the largest 10 particles that came through. Okay. Now we don't know anything about the implementation of a priority queue, but does that seem faster than an array list of a million things?
Yeah.
Does it seem faster than this idea?
Yeah,
probably because you're not comparing
because you just compare.
Yeah, if we think about what we're doing with the min PQ versus this, right? So let's say again, let's assume that I'm keeping track of just. I guess I could reverse the list. I don't want to do that. Let's say we're keeping track of the smallest things, right? And I get 7, right? Would 7 go in my list of 10 things? If I'm keeping track of the 10 smallest things. 7 should go in there, right? But what do I have to do first? I take 7, I compare it to the greatest thing, which would be 13. So I know it goes in the list, so I know 13 will come out, but then what do I have to do with 7?
put it in the right spot.
I have to go and put it in the right spot. Right? Do I have to do that with and I have to do the comparison every time? So let's say I get 15. Do I have to compare it? Do I have to compare every particle?
Yeah.
I have to check every
They're
particle,
not
so I'm
sorted.
doing the comparison. So here, I still have to do every comparison, but when I find something that should stay in the bag, do I have to do any comparisons?
No.
But it should say.
When it should, I just pop off the smallest thing, right? Throw it in the bag and I pop off the smallest thing. So there's actually no comparisons at all. I'm just constantly removing the smallest, right? And you could do actually one comparison check just to see, because I know that what's the top thing in a priority queue? What's the one thing I can interact with a priority queue? The smallest thing. And if it's the smallest of the 10 largest, can I just do one comparison to that thing?
Yeah.
Yeah, I can just do the comparison to that thing. So I do one comparison to the smallest. If it is smaller than that, I put it in the bag, right? And take off the thing that was at the top. That make sense? Okay. Bad implementations. Okay. So we could, now that we have a nice sense of how to use a priority queue, we could do this a couple different ways. What could be the underlying structure of a priority queue? We've just seen one, right? So a min priority queue could just be an array.
Array list maybe, please.
Could be an array list. Why would an array, well, would one be better than the other, an array list versus an array?
Probably the array list,
Okay. Why?
you change the size.
Do we care about changing the size?
No.
Not, that's with our example, we're just keeping track of 10 things and we don't ever have to change that size, right? We're just gonna, if something like, again, if something comes in that's should be in the 10 things, then I put it in the 10 things. So I don't need to change size.
So array is probably.
Array's probably better. It's probably 6 to 1, half dozen of the other. I've never actually thought about the difference between the two for this particular thing. Okay. Other ways we could implement this. Any thoughts? Again, we're trying to keep track of the smallest thing, right? So
Could we use, that's how we're, could we use a binary search tree for the things we're tracking? Then we would just compare the thing all the way at the bottom left, right?
okay, so if we had a binary search tree, right? Let me think about how to construct my binary search tree here. So I have 4, 2, 1, 3, 5, no, 8, 5, like that.
But then we have to like.
Is that a binary search tree? Just help me out, right?
Yeah.
Yes.
Pointers are all in the right place, like pointers. Got it. Okay, so you're saying if we had a binary search tree, we come into the tree and what would we do to find the smallest?
Go with one.
Just traverse left until we found something and take that. Okay? Any ideas better than that? To do it in terms of an array, let's think about a couple things here. With a binary search tree, what would be finding the smallest thing? What would the cost of finding the smallest thing be?
Log in.
Yep, so log n to find, what if I added something into this thing? Remember, we got add and remove are our real two operations. Yeah, add would be log n. Remove would be what? If I wanted to remove the smallest thing,
Same thing.
also log n. We have a slight problem, which we'll see in a minute, but okay. So add and remove would both be log n. For our array, if we had an array, what would remove be?
N, or if you remove the smallest thing, right?
We remove the smallest thing. Well, let's just do if we collapse this thing, right?
No.
Yeah, it would be 1, wouldn't it?
Yeah.
If it's sorted array.
It's sorted.
So remove would be 1. What would the add be?
But would you just set it to null and just set it to something else?
Well, yeah, so when you removed it, like, so now you do have the array list versus array. You could just set this to 0 or -1.
Yeah.
Or we could just say maybe we want to keep the space just in case we put something there, right? We do have a problem though, with remove, we don't have an issue because we can say that's null. What about add?
If it's in an array.
If it's in an array. So this was sort of a binary search tree.
Resize the array.
Array.
We add something.
Well, if we add, now if we're talking about like just some sort of random priority queue and we added something, we'd have to do a resize, yeah. Yeah, well, we'd have to resize. What else would we have to do? Let's say I added, again, if I added 6,
You have to compare everything.
I'd have to come in with 6 and find its place. What's the cost of that?
And
Yeah, so this, I'm thinking this is N and then possibly with the resize, like a little bit more than N. Right?
yeah,
Because what does resize cost me? What does resize cost us? Anytime we resize an array?
and right, because you have to redo everything.
Yeah, so N would also be, so resize would also be, I don't want to put it in parentheses, but we'd also have potentially the resize of. Okay. Okay, so we'll look at the bad implementations they do. Whoops, wait, why? What just happened? Oh, I went backwards. Okay, bad implementations. Okay, so we could have an unordered array. We get O of N for add, get smallest O of N, remove smallest O of N. We just said that. Pushing binary search tree, we get logs. Hash table we didn't bring up, right? We could theoretically try to do this in a hash table. Our add would be, what is our add always? It's always 1, right? That's the point of a hash table. But to get smallest, how would we get smallest out of a hash table?
You have to go through each.
Oh,
Then
You have to look at everything,
update.
right? Again, hash tables are good for what? Adding and if it's in there. That's what it's good for. It's not good for some sort of max or min algorithm.
Wouldn't get small be N squared,
For
hash table?
no, we just go through and just keep track, right? We'd have to go through everything. But we're just like, your typical min or max finding algorithm is what? You just set something equal to max and then just search through the whole thing to see if anything's smaller, right?
Yeah.
So that's not ideal. Okay. The only problem with a binary search tree is duplicates. Right? What if 2 particles are the same size? Can we deal with duplicates in a binary search tree?
No.
No, it's a set or it's a map, right? We can't have duplicates. So that becomes tricky here. Okay. So what we're going to use instead is called a heap. And I guess we jump right into it. Binary search trees would work, okay? But we need to keep them bushy, duplicates are awkward. So we're going to do this thing called a binary min heap. Our definitions are a little bit different of a binary min heap, but you probably want to write this down. So you can open up your computers if you're going to take notes, or you can take notes somewhere else. But you want to keep track of what a binary min heap is. So what are my 2 rules for a binary search tree?
Every
Small, right?
Yeah, so like, remember, I'll recreate this thing. So I go here, look at that. Oh, it's so fun to do that. Okay, there we go. So I know that everything to this side, to the left is
less than the rest.
smaller than the root. Everything to the right is larger than. And what else do I know about a binary search tree?
0, 1, or 2 children.
I can have 0, 1, or 2 children. That's it. That's my rules. Pretty straightforward. A min heap is entirely different. In this case, okay, we also have is this a binary tree? Do those look like binary trees? What makes something binary, first of all?
0, 1, or 2.
0, 1, or 2 children. Binary means like bicycle,
But
2 children.
Its left side is like 5.
Yeah, don't worry, but just the general structure. Don't worry about the numbers right now. Do these look like binary trees? Not search trees, binary trees.
Yes.
Yeah, they're trees, they have children, they can only have 0, 1, or 2 children, okay? A min heap means that every node is less than or equal to both of its children. In other words, 0 is less than 1? Is it less than 5?
No.
0 is not less than 5?
Oh, yes.
Yeah, okay. Is 5 less than 8?
Yeah.
Is 5 less than 8?
Oh, I thought you pointed
No,
out.
is 5 less than 8?
Yeah.
Just listen to the words. Okay. Is 1 less than 2 and 6?
Yes.
So is every node in this one less than or equal to both of its children?
Yes.
Okay.
Yeah,
Well, why is, 6 to the left of?
don't worry about that.
Oh,
It's not a binary search tree.
yeah,
We're making new rules here. This is simply a binary tree. It's a heap.
but it's still.
It's a min heap.
Yeah.
So is every node, there's two rules. Every node is less than both of its children. Is 6 less than 1? It doesn't, 6, sorry, is 1 less than 6?
More or less 6, yeah.
Yes. Are we saying anything about this direction? No, we don't care about the children's relationship to each other.
So that it could be either way.
This could be 6-2 or 2-6.
Oh, okay.
Yep. Okay. Missing items only at the bottom level. Okay. All nodes are as far left as possible. So I'm not missing any nodes. And if I am, they're as far left as possible. Okay. So is this, actually, you know what we're going to do? I should have done this differently. Let's try this. Okay, there's our two rules. Is this a min heap? Is this a binary? Is this a min heap? What's that? By itself.
Yes.
Yes. Why? Is every node less than both of its children?
Yeah.
Yes. Is it complete? Missing items are only at the bottom level, right? And pushed as far left. Yes, it is. Okay, how about this one? We already looked at it. Yeah, right? 0 is less than 5 and 1. 5 is less than 8. 1 is less than 6 and 2. Are there any missing items? Nope. Okay. Oh, let's move this thing out of the way. In the butt, right? How about this one? It is missing items. Is at the bottom level?
Yeah.
It is. Are all nodes as far left as possible?
So it's
Still counts. Okay, that still works. How about, oops, this one? Okay, so we know the first property is 0 less than 5 and 1.
Yeah.
1 less than 2.
1 is less than 2.
Yeah, 8's both greater than 5. What's the problem?
2 is all the way.
2 is on the right child, it's not the left child. Okay, and you'll see why this is important, hopefully soon. How about this one?
4 is 5.
5 not less than 4, it lacks the min heap property. Okay, this one we call incomplete because that's just not in the right place. Even though it's not like I need to fill in that space with something else, it's incomplete because 2 should be on this side. Does that generally make sense? Cool. What time do we go to? Thank you. Right, 35. Okay, which ones of these are min heaps? You're counting how many of these are, but I could also say A, B, C, and D, which ones are. So write down which one of these you think are min heaps. All right, so we're gonna go around the room. Mary, is this one a min heap? Anyone want to disagree? It is in min heap. Okay, Logan, this one, min heap. No? Anyone want to disagree?
5 is the bottom, 6 is bottom.
Okay, Logan, why did you say no? Wait, does anyone agree with Logan? First of all, everyone's against Logan. All right, sorry, Logan. So Logan, why did you say no? Help me out.
Can I see the properties?
No, go ahead. Just say what you're going to say first. Doesn't look. Come on, tell me. Give me. Be more specific. Why? There's your properties. Logan doesn't think so. He just can't put his finger on why.
I'm
Why?
it's supposed to be in the balance.
What do you mean? Be specific. Come on, look at so obviously less, like we have the less than. Yeah, great. How about part 2?
Oh, wait.
Now, Logan's right. He's correct.
The second child, right?
Yeah, it's not complete. So what, so you just gotta be more specific with what you're saying. So what are you saying? Yes, you do. Just say the words. What is it missing? Yeah, we're missing a child over here, right? Again, missing items only at the bottom level. Are we missing a right child? Yeah, right? So how can we fix this? What should be there? Should be what in this case? If I had to move something quickly and easily. 8. Yeah, 8 over as a right child would make the most sense because then I still have a left child over here. Then this level would be complete. This level would complete. My missing item would be at the bottom level and everything would be pushed right. Okay. Alex, how about this one? Why not?
Because like the parent, the top one is greater than the children.
Yeah, all the way down this left side, right? That's problematic. Whoop. Yeah. Tony, how about the right one there?
That was good.
That one's good. Yes, it turned green a second ago. Okay.
Why? One child.
Yes, but where is the child? Right, it's on the bottom level and it's on the left, so it's okay.
That just looks weird though.
It does look weird, but it is a min heap property. Okay, so this one's correct. That's incomplete. That lacks the min heap property. Okay, so priority queues become super helpful. Sorry, heaps become super helpful for your priority queue. Let's think about this. How would you support get smallest? What do we do to get smallest off this particular? This is now. Is this first of all? What is this thing right here? It's a min heap. Is it appropriate? Is it appropriate min heap? Is it a good min heap? Return the root. We're done. Okay. All right. How about add? How are we going to add something? We want runtime that's logarithmic, and we want to add something.
Then, well, we have to add to the right, right? Because everything has to be on the left.
What do you mean to the right of what?
5.
So right child of 5. So we know we're going to have to add whatever we're adding here. Yes?
Oh, rotate.
Well, this becomes actually pretty easy if the number's what?
6.
If it's 6, right? 6, boom. Are we done?
Yeah.
We're done. Yes? But we know it has to go there. What if I want to add 2?
Move 5 down. Well, 2 replaces 5.
Where am I putting 2 to start?
To the right of 5.
Same place?
No.
Oh, we don't
Two
consider.
there?
No, never mind.
So,
You have to.
When you
add 2 and then you rotate.
Let's be careful with rotate. I know we've used rotation, but do I need to rotate?
no.
Rotate would mean that I'd shift 2 up and then what?
5,
I don't know.
6 would go on the same.
5 goes to the left.
Yeah, 5 would go to the left and 6 would drop down. Is that what I like? No, we don't want that.
We swap.
Just swap.
Oh.
So what do I do? What do I ask 2?
Swap with 5.
Well, I say is 2 smaller than
5.
It's parent.
its parent? If it's smaller than its parent,
Swap.
swap. So this would become 2 and this would become 5. Are we done?
Yeah.
Yeah, we would actually theoretically, if we're writing a program, what would we want to do here with 2? If 2 were here, we just put it there. What do we want to do?
Then
Say louder, Mary. Just make sure it's smaller than 1.
Greater than 1.
That too. Yeah. It's a Monday.
Oh,
Okay,
yeah, but
so I just want to make sure that it's greater than 1. As long as it's greater than 1, it just stays put. So you drop it in where it should go. I have to make sure it goes into the empty spot to the leftmost.
so we need to compare stuff.
And then another reason we need comparable. And then we compare it to its parent. If it's smaller than its parent, I move it up. Right? As soon as it's no longer smaller than its parent, I stop and it's fixed. Cool. We're good with that one. Do we want to see the automated demo? I just gave it to you. You do? All right, we insert 3. Right, 3 goes into the empty spot. What's wrong?
5 smaller than.
It's smaller than 5. So we go through, and we call it swimming, just to be clear. That's a good picture.
Twice here?
Yep.
2 5s.
Yes,
Yeah, you have to check twice.
we have to check twice.
They call it swimming.
Swimming. It's going to swim up the tree. Why are we swimming up a tree? I don't know, but we're swimming up a tree. Okay. We should be climbing up a tree, but typically it's called swim. Okay. So we're going to swim up the hierarchy. We switch 3 and 5. We compare 3 to our another 5, right? The second one up. We switch and
No, compared to.
we compare to the root. We compare to the parent. It is no longer, oh, I'm in the right place. Okay. Then if we want to add another 5, we just do the same thing. Okay. Add to the end of the heap. Then we compare, we swim, compare, we're done. That's it. That's add. Pretty straightforward.
So it doesn't matter if we're missing only one, like, we can miss more than one thing from the heap as long as it's on the bottom. Like with this technically.
Yeah, right, because we're missing 3 things.
Yeah.
That doesn't matter, as long as the only things missing are on the bottom row
And,
and everything's pushed as far left as possible.
okay.
And you'll see why in a moment. Okay,
How do you find like, how do you know?
how do you know to stick it right there, right? That's what you're asking?
Yeah.
It's a great question. And intuitively, it's hard to think about, like, so right now with what we know, how would you do it?
Like, just go through every bottom, the leaf nodes and find like.
Yeah, so if we started here, let's go back actually, right? If we come to this one here, right? If we come here, what do we have to do? We'd have to first go left. Well, do we have to go left here? If we've structured it properly, we'd go right,
Then go left.
then we'd see if it has one child. If it has one child, if it has no children, I'd add it.
Go left.
If I, to the left, if it has one child, I'd have to add it to the right.
Is there a faster way to do this?
Yes. But it's the way it's not the way we're doing it, it's the way we structure it. Which will make sense, hopefully, in a minute. Because then, right, when we come down to the harder one, we get here, where do we go now? We don't go left. We go right. We go, well, do we go left first? We check left, but then we'd have to check right. But it's got 2 children. But then we come here and then we have to check whether it's got a left child. And if it doesn't have a left child, then we put it there. Complicated? Yeah, recursively, we could probably make it sort of interesting, but it's not particularly easy, right? It's certainly not as easy as we'd like it to be. Okay. Okay, so back here, I need to go back. Oh, how do I get out of? Interesting. Okay. Drop this down here. Okay, how about delete? So we got to think through delete here. Remove smallest. Runtime has to be algorithmic.
The root, right?
It's the root. It's always going to be the root. So the question is then, what do I do to replace it and keep my structure?
You have to check its children first, right? Because those would be the first thing.
Yeah, but I run into, so it's sort of problematic because, right, so we're going to remove 3. Actually, let's do this over here. Let's make a min heap and do this over here. So what are my properties here? Let's say I know that this is a 1, this is a 3, this is a 2. Does that work? Here, let's just make it more interesting. Is that a min heap?
Yeah, yeah.
Okay,
Yeah.
so let's remove 1. Which thing should end up top? 2. So what if I do that? But remember, this has got 2 children, so what happens now?
The smaller one goes.
You want the smaller one to go up, what happens to 13?
Oh,
it goes to the right.
It has to shift that way, so how many steps did that actually take?
4.
Right? It's sort of complicated, so if I think about this one, which one would I move up? 3, but if 3 comes up, then what happens?
5 goes.
Okay, so we're gonna end up with, what did I just do?
Then we're incomplete on the second one.
Yeah, but then we totally screwed up the whole structure, right? Because 3 comes up here.
Then we move 8.
So let's say this is a 3, this becomes, what do we say, 5, 6 would have to move over here, but this doesn't exist.
So we move 8.
But then I could move 8 over here.
How would we
Oh, that's ugly, isn't it?
how would we even move move 8 all the way over.
Yeah, how do we even go find 8 to move it over into the right spot? And then I'd have to make sure that it's less than or greater than 5. Not so fun. Think of another way.
You have to like replace it with like 8 or something.
What do you mean?
Like it's like the middle left.
We know that I want to keep the structure, right? What space, like if all things being considered, to keep my min heap property, which thing do I want to go away, Logan? You just said it. Which node do I want to go away? The 8. I want that. That's the only thing I can remove out of this thing to keep the min heap property.
It's the bottom right.
As well as the last one in the tree.
But it's.
So if we
Put
replace
8,
like if we
at
replace
3.
8 at the
And then
here, like every
We're gonna, you guys are both right. We're gonna swap 8. We're gonna put 8 up here. We're gonna remove this. 3 goes away. Now 8's up here, right? And this is gone. Actually, we're gonna I think it'll be easier to do over here. So let's say I remove, what did I just do over here? Okay, so I'm gonna remove 2. What do I do?
Put 8, put 15 at top.
So this is gonna go up here.
and then you have to check.
You have to
I kept my structure.
check the smallest
Check the smallest of these 2.
and swap.
Swap.
Then again, check on the swap form. Yeah. So, yeah.
Now it's valid.
Now it's valid. So when we added, we did what? We swam up the tree. When we remove, we swap and swim down. That's it. Is that in your head, is that reasonably easy to sort of wrap your head around what code might look like? So hopefully it's sort of making sense at least, right? What is this? Get smallest, return, assassinate the president. Okay, so place the new, so he has some, yeah, this is his analogy. Right, so his analogy for add is we take the newest employee, right, put them in the last position and promote them up. That's just swimming up, right? The remove smallest is we take out the top of the company, right? Put the lowest placed person in the organization at the top, and then just swim them down to where they belong. Okay. Okay, this is where this becomes really interesting. 35, we get 7 minutes to make this interesting. How do we implement this thing? Right, so the question was before, like, how do I know that this node's the last node? So how could I implement this thing actually in code for the backing structure of this? What would the backing structure of this thing look like?
First, make it like a BFC, right? Where you just change the first rule. You just change it instead of left is the last. You just change the follow the every node is less than or equal to.
So we just change the rules. We create a binary search tree type structure and we just change the rules, right? So instead of left and right, we just say that all of our children have to be bigger than we are.
But that doesn't account.
You always have to flip some sides. Or change some sides.
What do you mean change
Like,
signs?
instead of it being like, if. Like for, I can't explain it, there's like, instead of it being like. I can't explain it.
Okay.
Yeah.
Okay, so we're going to change the structure of a binary search tree. Then the problem though is which part of this thing?
The bottom one.
Yeah, how do I like, so right now, where would I add to?
You would go there.
Here, and then I'd swim it up. Right, and then if I added 1, I'd have to add 1 here, right? But actually, let's add 3, right? So if I add 3, do I have to do anything?
No.
But how do I know where to go?
And you keep recording the location of the last, like the last node.
So we could keep track of the last node, right? And see where it went and then go to that place. Can you guys think of a way you do that in Java? Well, we could keep track of children, right? So we can keep track of a node, and then if a node has 2 children, we know it doesn't go into that range. We'd have to check this node, does it have 2 children? Does this node have 2 children? I know that the first child will go in the left spot, second child will go in the right spot. Right, so we can make that work. So one alternative would be this thing, right? We have a couple different things to do this. We'd have this structure. I don't know why he put 3 nodes in the bottom, but whatever, okay. Can we have 3 nodes in the bottom? No, we can't, but whatever. So you can sort of visualize the way this would look. But we have an array for each node, and then it would have a left, middle, and a right. In our case, it would just have a left and a right child, right? So we'd have sort of an array of 3 things. We'd have W and then a left and right child. Okay. Our BST map essentially used this. We kept track of our right and left child, right? Did we do it in an array or did we just keep track of it inside the node? Inside the node, right? So we could do that. Okay, so this is one alternative. This is another alternative, which is essentially the same idea, but now we have a W with just 1 pointer. That pointer points to an array that points to each of its children, right? So we have sort of an intermediary step here with an array of children, and the array in each box of the array points to a child. Okay, do we like this one? Would this allow us to keep track of where it was empty?
Yeah.
This would be a better thing because I could simply go in and say, okay, which one of these pointers is null?
Then we would add to the right.
And then we just go to that spot and add to the thing. So it solves our problem, okay, in a fairly clean way. Do we like it?
There's 3. We'd have to keep.
Yeah, we'd have to, like, I don't know why he did that, but let's assume it's just 2 nodes, right? A right and a left child, because we know that we can't have 3 nodes. So it would just look like that, okay? We could do, he also has this sort of interesting implementation of, we're going to point to the left child, which again would make sense, but then this points to each of its like siblings, right? So our left child would point to the right child. And you'd sort of go down the tree this direction to make sure if we had a left child, then we know we need to check this child, right? And we could just keep doing that recursively just to make sure that all the children were there. Okay. What I'd like you to do, and we'll do this for homework, is can you think of another way of doing that? These are our 3 methods so far. And then what did we do with our, do you remember the structure where we kept track of the parents in an array? Remember that?
Is that what we did?
It was in disjoint sets. So disjoint sets, remember, had this, right? So let's think about what we have for keys. And I would change this slightly. But we have our keys, W, X, Y, and Z. And then we know the parents because W's parent is
Not self.
itself. And X, Y, and Z's parent is
W.
also W. So we just keep track of an array of the parents.
Oh, yeah.
Is this ringing any bells?
And we kept like the size and that one. index.
Right, so we, W would probably be more appropriately like 3 in this case, or 4, right? Because we have itself, it would start at 1, and every time we added a node, we get 1 more space there. I'd either like this to be a -1, so we know it was the root. Because all zeros, which one's the root? Right? So this should be a -1 or it should be 4, one or the other. And then we've laid out this sort of in a more aggressive way, right? So we have all these things. We have all these nodes, they have some letters in them. Clearly we're basing our min heap property off the number, okay? Because, no, actually I take it back,
It actually makes more sense
right?
this way.
Yeah,
Because only the bottom row can like, I'm missing child.
yeah. So now where do I know I'm gonna put something?
End of the array.
The end of the array. Yep, right? If I add something, I have to put it here. Right? This solves all of our problems of where to put things. It also becomes really quite cool because if you look at these numbers, right? If we say that K is the root and we give this a -1, what do you notice about the numbers of the parents?
2.
I get these two, the parent is 0, these two, the parent's 1, these two, the parents are 2, 3, 4, and 5, and then 6. Yeah?
Yeah.
So your job for homework is to figure out, okay, how do I get mathematically to a parent?
To a parent.
To a parent.
What do you mean, like get to a parent?
Well, I can go, the trick here is this is all well and good. But when I go through this, I need to be comparing children to parents, right? That's the big piece of the min heap is comparing children to parents. I want an easy way to go in and say, hey, are you my parent? What's the easy way down here to say, hey, are you my parent?
Just compare the index, the values, and
What do you mean, Daniel?
like 3, like index 3 has a value of 1.
Yep.
So just compare like just 3, but like if you on the left of that min heap, sorry, I think I can't see it, but like B is less than E, but it's just they're like in the same spot, right? Could you compare them like that?
Simpler. I'll be honest, you should be able to look at this, forget about this actually, and figure out a mathematical way to get from any child to its parent and vice versa. Tony, you're not in your head. How do you do it? Okay, that's homework.
Maybe like divided by
Ah, divided by 2. I'll let you think about that for homework. And I'm also going to give you a leak code. Have an awesome day. Hey, good luck on AP exams. Any of you gone on Wednesday for APs? Okay. All right.
Wait, let me just check. I'm an AP